Dear students, welcome to EPG Pathshala. In today's module, we are going to discuss on solar ponds. Solar pond is one of the approach to harness solar energy. Due to the prevention of the convective currents, it can harness the heat energy in more efficient way than a normal pond does. In India, the first solar pond was built at Bhuj. This solar pond can be used for different industries, for heating and cooling of the buildings, for the desalination process, etc. So in this module, we are going to discuss on what is a solar pond, what is its working principle, what are the different types of solar pond, what are the applications of solar pond. Let's start with solar pond. It is a natural or artificial body of water for the collecting and absorbing radiation energy and storing it as heat. It is known as the solar pond. A solar pond of shallow depth with a radiation absorbing bottom, that is a black plastic bottom, is one of the example of this solar pond. The heat loss to the ground is reduced with the help of a bed of insulating materials. So the solar radiation is entered through a cover which is made of transparent fiberglass, which is placed over the pond, inhibiting radiation and convection losses. So it prevents these losses. So once the radiation comes into the pond, it is trapped there. The water in the shallow pond gains the temperature uniformly, but it's only to a fewer degree. The energy is stored in low grade thermoform, that is 60 to 100 degrees Celsius. So we can define a solar pond as, more clearly, it is an artificially constructed pond in which significant temperature rises are caused due to the lower region, in which significant temperature rises are caused to occur in the lower regions by preventing the convection. These are also known as shallow solar ponds. What are the types of the solar ponds? The solar ponds are divided into two main categories: non-convecting ponds and the convecting ponds. Non-convecting pond, it reduces the heat loss by preventing convection from occurring within the pond. There are two types of non-convecting ponds: salt gradient ponds and membrane ponds. Salt gradient pond has three distinct layers of brine, that is a mixture of salt and water of varying concentrations. So the salt gradient pond is a body of saline water in which concentration increases with depth from very low value at the surface to near saturation at the bottom. The stratification of the concentration is achieved by dissolving a salt at different salinity levels. The salt gradient solar pond is a body of saline water in which concentration increases with depth. So that is a salt gradient pond. Membrane ponds, this inhibits the convection by physically separating the layers with thin transparent membranes. Convecting ponds. This is the second type. This type of pond prevents the evaporative losses with a cover over the surface of pond. In this shallow solar pond, pure water is enclosed in a large bag that allows convection but hinders evaporation. The bag has a blackened bottom, it has foam insulation below and two types of glazing, the sheets of plastic or glass on the top. The sun heats the water in the bag during the day. At night, the hot water is pumped into large heat storage tank to minimize the heat loss. Excessive heat loss when pumping the hot water to the storage tank has limited the development of shallow solar pond. So most commonly used the ponds are of non-convecting type, and especially the salt gradient non-convective ponds. So, we will see what are the characteristics of salt used in the salt gradient ponds. The salt used in a solar pond for creating the density gradient should have these characteristics like it should have high solubility, no variation in solubility with respect to temperature. Its solution must be adequately transparent to solar radiation. It must be environmentally safe. It must be environmentally friendly, safe to handle the groundwater. It must be available in abundance near the site so that it reduces or it won't affect the cost. It must be inexpensive. The stability of a non-convective layer in the presence of temperature gradient can be maintained by creating a sufficiently steep salt concentration gradient. In order to generate the initial salt concentration gradient required to prevent convection, the usual practice is to fill the pond with several layers of salt solution, with the successive layers changing stepwise in concentration from near saturation at the bottom to the fresh water at the top. For a typical pond of 1 meter deep, one might use 6 to 8 layers. Less layers can be floated successively on top of existing ones, or successively more dense layers can be put in at the bottom, pond bottom, flowing in as undercurrents and gradually lifting the whole pond. Because of the turbulent mixing and molecular diffusion which occur during filling, the staircase type concentration profile evolves into a smooth, nearly uniform concentration gradient. The typical value of salt concentration at the top surface is 20 kg per cubic meter, that increasing to 300 and 260 kg per cubic meter for magnesium chloride and sodium chloride respectively at the bottom. So, from 20 to 300 for the magnesium chloride and 20 to 260 for the sodium chloride. It is necessary to add periodically concentrated solutions at the bottom and wash the surface with fresh water to maintain the concentration gradient in presence of diffusion effects. So, this is how the salt gradient solar pond works, or the structure of this solar pond. Let us see what are the zones of this non-convective solar pond. So, the solar pond has a plastic lining at the bottom. The plastic liner should be made of butyl rubber, black polythene and hapalon reinforced with nylon mesh are commonly used. The salt gradient solar pond uses salts like magnesium chloride, sodium chloride or sodium nitrate. The most commonly used salt is the sodium chloride because of the earlier characteristics which make it more suitable for this use. The stratification of solar pond is the non-convective solar pond are divided into 3 zones. One is the surface convective zone, or it is also known as upper convective zone, abbreviated as UCZ. Non-convective zone, that is NZZ, and the storage zone or the lower convective zone, that is LCZ. The surface convective zone is of depth 0.3 to 0.5 meter and the salinity should be less than 5%. In the non-convective zone, from 1 to 1.5 meter and the salinity increases with depth. In the storage zone or the lower convective zone, the depth is 1.5 to 2 meter and the salinity is of 20%. The surface convective zone, it has a small thickness with uniform concentration, that is we have seen 10 to 20 centimeter with uniform concentration, that is less than 5%, and a uniform temperature near to the ambient air temperature. You can see in this figure 1, 2, 3. The 1 is the surface convective zone, 2 is the non-convective zone and third one is the storage convective zone. You can see the thickness increases from 1 to 3 third zone, first to third zone. in the non-convective zone is much thicker and it occupies more than half the depth of the pond. In this zone, both the salt concentration and temperature increases with depth. This zone acts like insulator and prevents the heat loss in upward direction. In the storage zone, that is at the bottom, that is 1.5 to 2 meter depth, with the concentration and temperature here it also nearly constant. This is the main heat collection and storage pond. That is the third zone, that is storage zone or the lower convective zone. And the storage of heat increases with the depth. So you can see in this one, there is the brine, the return of brine as well as the hot brine is produced. What is the principle of the non-convective solar pond? Collection and storage. The collection area for the solar energy in solar pond with a plastic liner at bottom is the water present in it, that is water present in the 1 to 2 meter deep. The salt gradient non-convective ponds maintain the density gradient with the dissolved salts. The portion of the incident solar radiation that reaching the pond is absorbed by the water and the rest is absorbed by black bottom. The rest penetrated is absorbed by black bottom. In freshwater pond, the expansion and rising to the surface occurs after heating up of bottom layers. The convective mixing and heat loss create very low increase in temperature in this pond. This can be excluded by the salt concentration gradient in the pond that overcomes convection and thereby thermal expansion in the lower layers. The salt concentration ranges from 20 to 30% at the bottom to 5% or even less to 0 at the top. This creates a density gradient with heavier layer at bottom and lighter layer at the top. The saline water with low conductivity act as an insulator and so develop high temperature in the bottom layer. The solar pond traps 10 to 20% of the solar energy heating its surface. Hence, each square meter of pond surface area can supply 1/2 to 2 gigajoules of thermal energy per year at a temperature from 40 to 80 degrees Celsius. The highest temperature ever recorded in a solar pond is 108 degrees Celsius set in the summer of 1980s at the University of New Mexico. A flat plate collector of the same area would be twice as efficient, but cost is 10 times higher. So the first one, we have seen the collection and storage. Now the second part is the extraction of thermal energy. The energy is stored in the low-grade thermal form of the lower convective zone. We have seen the three zones, the upper convective zone, the non-convective zone and the lower convective zone. So once the collection and the storage, the collection of the solar energy occurs in this pond, it is getting stored there and has to be extracted. So the energy stored in low-grade thermal form of the lower convective zone has to be extracted. The convection in the zone is due to the process of heat extraction, which is accomplished by hot brine withdrawal and cool brine return. So it is not practical to cover the bottom of pond with an array of pipes acting as heat exchanger because of the cost will increase sharply in the case of large ponds to the size of about a square kilometer. Unless there is a convection to around the pipes, the heat transfer from the stationary hot brine to the fluid in the pipes will be very poor. So it is not practical to cover the bottom of the pond with these pipes. So the thermal energy stored in the lower layers of water need to be extracted, and the hot water can be extracted from a solar pond without disturbing the concentration gradient. For this, water outlet at the same height as the water inlet was installed. Hot brine can be withdrawn and cool brine returned in a laminar flow pattern because of the presence of density gradient. For small or model ponds, heat exchangers consisting of pipes can be placed in hot lower layers. But this entails not only the initial installation cost, but the continued pumping losses associated with the heat transfer fluid. Thermal energy from solar pond is used to drive a Rankine cycle heat engine. Hot water from the bottom level of the pond is pumped to the evaporator. You can see in this figure, the hot water from the bottom level of the pond is pumped to the evaporator where the organic working fluid is vaporized. The vapor flows under high pressure to the turbine and thereby expanding through the turbine wheel and the electric generator linked to it. The vapor then travels to the condenser where the cold water from the cooling tower condenses the vapor back into a liquid. The liquid is pumped back to the evaporator where the cycle is repeated. A 2000 square meter solar pond equipped with a 20 kilowatt engine is constructed in Australia for the electric generation. The advantage of solar pond, especially the saline gradient non-convective solar pond, is that it is not affected by the diurnal changes, seasonal changes, cloud cover and the ice cover. And the factors like location, water clarity and temperature influence the heat trap in solar ponds. Let's see what are the applications of solar ponds. These are mainly used in the thermal applications like heating and cooling of the buildings. The solar ponds are capable of storing large amount of heat energy in its lower convective zone. The operation of solar ponds is simple and is comparatively less expensive. Some of the researchers reported that this solar pond technology offers heat at a cost of $0.010 per kilowatt hour. And they found solar pond house heating systems effective if that pond is used to supply thermal energy to many buildings. Power generation. The electricity generation from the heat trapped in solar pond was either by driving a thermoelectric device or an organic Rankine cycle engine. In this process, a turbine is powered by evaporating an organic fluid with a low boiling point. This power generation is very useful in areas with level land receiving enough solar radiation, with soil factors suitable for solar pond construction and operation. The solar pond power plant uses halocarbons or hydrocarbons as the fluids. The significant potential for the electric power generation from small solar ponds through a simple and passive device incorporating thermosiphons and thermoelectric cells. The scientists or the researchers reported that electricity production of 36.25 million volt from the solar pond with water as a working fluid, and if we use some working fluid like R134, it has electricity generation of 234.25. In salinity gradient pond with a surface area of 7 meters square and a depth of 1.3 meter and this research was carried out at the Rajmangala University of Technology in Thailand. They reported these values for the power generation from solar ponds. Another application is the industrial process heat, that is IPH. Here the thermal energy required for different industrial process directly utilized from the solar ponds. This was used in drying of crop products, vegetables, paper industry, and it is used mainly as a fuel saver in these industries. Another application is the desalination. Multi-flash desalination along with a solar pond is useful in the purification of saline water and make it potable for the drinking purpose. The distilled water can be produced from multi-flash desalination plant operating below 100 degrees Celsius coupled with solar pond. It has been estimated that about 700 cubic meter per day distilled water can be obtained from a pond of 0.31 square kilometer area with a multi-effort distillation unit. The water produced by this technology is 5-fold than the conventional solar still. So that is used for the desalination and using it for the drinking water purpose. And it can also be used for the salt production. These are found helpful in recovery of salts from brine water and can also use for heating up the animal houses. Solar ponds in India. The artificial solar pond was started in Israel in Israel in 1958. Central Salt and Marine Chemical Research Institute CSMCRI at Bhavnagar in 1973 under the leadership of Dr. G.C. Jain has designed a solar pond for use in the production of salt. This is known as Bhuj Solar Pond. Bhuj Solar Pond at Gujarat, constructed in collaboration with TERI, Gujarat Energy Development Agency and Gujarat Dairy Development Corporation, was the first solar pond in India to have connected itself to an industrial process. It was supplying heat to Kutch Dairy from an area of 6,000 square meter. The construction was started in 87 and completed in 93. It used locally mined clay and plastics as the lining to reduce the cost, and it was able to supply successfully 80,000 liters of hot water daily to this plant. But today it is not operational due to financial supports and other government policies. El Paso Solar Pond, University of Texas and Beit Harva Pond in Israel are examples of other famous solar ponds in the world. The limitations are the solar to electricity conversion is not sufficient. The conversion is generally sometimes less than 2%. The shallow solar pond is capable to heat up only a few degrees of temperature. The variations in the temperature also occur in deeper ponds. The shortcomings of the conventional gradient solar pond has been overcome by the solar gel pond. It is the non-convective salt gradient layer. In this pond, the non-convective salt gradient layer is replaced by a transparent polymer gel layer that floats on a NaCl solution, that is seawater, which is used in the storage zone. And a saltless solar pond, it is a convective type. These two type of ponds, solar gel pond and saltless solar pond, can overcome most of these shortcomings of this conventional salt gradient solar ponds. So to conclude, in this module, we have discussed about the solar pond. What is a solar pond? It is an artificially constructed pond. Sometimes natural pond can also be used for the collection and storage of solar energy. Here, it prevents the convective currents so that the heat trap in it is stopped there. So here we have seen different types of solar ponds like non-convective and convective. Under non-convective, there are two types, salt gradient and the membrane type. Here we have seen that the most commonly used one is the salt gradient solar ponds. We have seen some of the characteristics of the salt to be used in the salt gradient ponds. And we have seen the different zonations or the stratification of these salt gradient ponds, like the upper convective zone. We have seen the non-convective zone, and the third one is the storage zone or the low convective zone. We have seen that these solar ponds are more cost effective than the solar collectors. We have seen different applications of the solar ponds like heating and cooling of the buildings, the industrial uses, desalination, the salt production, as well as some the heating of these animal houses. We have seen that the factors like the location, the water transparency and temperature affects the performance of solar pond. We have seen there are some limitations with respect to the solar ponds, and it can be overcome by some advanced form of solar ponds like the solar gel ponds and the saltless ponds. In India also they constructed the solar pond in Bhuj. Right now it is not operational, but we have already constructed it and it was successfully supplying this hot water for the industry, for a dairy industry at the Bhuj. Thank you.